Welcome to Last Minute Tonight with yours truly, Kishkandy. Thank you so much for joining. Yes, you heard it right. It is Last Minute Tonight, literally last minute. This video was edited a minute ago. This presentation was finished today. Guess what? This presentation was so last minute that you didn't realize our show's name was cut wrong. Let's fix that, shall we? Thank you. Our main story tonight is wastewater. Wastewater is a huge problem in our world. The definition of wastewater is the water that emerges after fresh water is used by human beings for domestic, commercial, and industrial use. In this presentation, however, we are going to focus specifically on sewage water. Often, an undermined issue in the conundrum of wasted water is sewage. We are the production houses of sewage on a daily basis and can contribute up to 135 liters of it per day per person. Understanding the reason and possibility for such a fact is like trying to understand a Christopher Nolan movie. Whatever you're watching is true, but it makes no sense whatsoever. Having a conversation about sewage water is quite useless without understanding the implication that it has. Let's keep sewage water aside and let's talk about the polar opposite, fresh water. The need for fresh water today is shooting through the skies. Today, there are up to 783 million people who lack access to any source of clean water. Yet, to juxtapose this fact, we land ourselves in the midst of soaring rise of water in agriculture. It is estimated that an astonishing 95% of fresh water is consumed for irrigation. Now, that is a problem. The nuances that exist in water consumption are a whole lot like that of a monopoly-dominated economic system. The simple fact is that agricultural water does not require fresh consumable water because of the nuances in its constituents. It is now fair to say that it's crucial to bring a more reusable alternative into play. This is where sewage water comes back. Almost none of it is ever effectively used for any constructive activity. At the moment, sewage water is as used as a bachelor's in business. It seems to play into the ring of logic to modify the compositions of sewage such that it satisfies the needs of plants without causing any measurable harm to them. Using this idea, the plethora of clean water that can be saved is massive. This becomes the aim of the project, to develop a methodology to purify the sewage to a level such that it becomes operational for irrigational uses. But before that, let me explain how a current wastewater treatment plant generally works. A normal wastewater plant has three different stages: a primary, a secondary, and a chemical purification stage. However, before all this, there's a preliminary stage, which is broken down into three more processes. The primary stage is further broken down into two more processes, and the chemical purification is broken down into two more processes, which adds up to a total of 11 processes. The number of processes is so high that even Snoop Dogg won't be able to reach it. First, the preliminary stage, also known as gathering the tissue and the lotion. The preliminary stage is broken down into three processes. The water first flows through a screening process, which traps clothing, sticks, and small animals. This is followed by a skimmer process that removes all non-dispersible material, where according to one fact, 50% of it is toilet paper, 25% of it is baby wipes, and the remaining 25% is a mixture of condoms, cosmetic wipes, and tampon applicator. Finally, the water flows through a grit chamber, where the sand and gravel are removed by the beauty of sedimentation. Then water flows to the primary stage. First, the water flows into a circular basin called a primary clarifier, which has an angular acceleration that slows down the flow of sewage. This allows the particle in a suspension to settle to the bottom due to centrifugal forces. The primary stage also involves a skimmer that removes fats, oil, and grease. No, not that grease, that grease. All these particles are then transferred to a digester where it is treated with anaerobic bacteria to digest the waste. After the primary process, the water flows to the secondary process. Here the water flows into an aerator basin where air is added to foster an efficient environment for microorganisms to degrade any remaining organic matter which may not have been filtered in the previous process. Any excess waste is coagulated and pumped to the digester mentioned earlier in the first process, in the primary process. Finally, after physical purification, the water goes through a chemical purification. This again is split into two processes. First is chlorination, where chlorine is added to the water to kill any harmful pathogens. Generally, water is then dechlorinated and disposed into water bodies. However, some wastewater plants have an extra treatment to remove any phosphates, any heavy metals, and any nitrates. This process, however, involves multiple processes and costs a lot. This is where we come in. We believe that we have a cheaper and more efficient processes that allows the wastewater to be reused for agriculture. And now this. we have our underpaid, overworked, deep-deprived researcher, Dr. Pranjal Mathur, to share his thoughts.
Hi. Psst. Hi, my name is Dr. Pranjal Mathur. A long-known fact is that aquatic plants have existed for millions of years as a natural microfilter for removal of wastes. Aquatic plants are typically inbuilt into an ecosystem in such a way that they create a homeostatic environment which allows a community to be established. Now, as far as the decontamination of wastewater is concerned, there is very little disagreement on the ability of a very well-known species known as the water hyacinth. The water hyacinth is a very impactful plant because it reduces the content of nitrates by an upwards of 77%, phosphates by 18%, and also reduces the biological oxygen demand by 91%, while reducing the chemical oxygen demand and total dissolved solids by up to 87%. Although other aquatic plants do reduce these quantities, they tend to lack the ability to reduce them altogether. In a sense, this plant is the best in its league. Of course, it also has the advantage of being much cheaper and readily available in about 4 different continents. Moreover, the hyacinth is one of the most fast-growing plants. This means that the roots of the plant grow rapidly, increasing the surface area for absorption and therefore allowing more contaminated water per unit time to have its toxins absorbed. Yet at the same time, the growth of the shoot is exponential, which means that their lifespan in the plant reduces a bit. Of course, I am a fan of this plant and hope that this can be used on a larger scale. I feel that it is a natural form of purification that can quite easily be adapted into an operational purification plant. We work with a wastewater flow line that comes from a centrally governed source. This, of course, is connected to most domestic pipelines and contains waste from houses, public buildings, and hospitals. This water contains high BOD, COD, and TDS levels. The aim is to reduce these quantities so that the output water can be used for irrigational purposes. This is where the water hyacinth comes into play as a filter to help in decontaminating the input water. It is noteworthy that the water that leaves the hyacinth system will be purified to a certain extent. This water will not be safe for consumption because it will still have relatively high contents of the aforementioned wastes. Also, this process meets the requirements of water quality for plants by deviating about noted literature values by under 1% of deviation. Treatment by hyacinth, however, is not enough to remove pathogens inside the water. For this, a dedicated layer of UV lights are used at wavelength of 254 nanometer and intensity of 12 millijoule per centimeter square. This ensures that the water used for irrigation will be safe for the crops. The big question now is, how much water can we retain, and if so, at what rate?
According to a secondary source, one of the first aquatic plant-based purification systems occurred on a 1-hectare design. We, however, adjusted our scale into a more compact design that can be adapted for a smaller area with the potential to multiply output with a greater given area by having numerous reactors. Our plant is a building with a 25 times 25 meter base indicated by the blue that is 10 meters high. The plant is divided into 11 levels indicated by red. Each level is 0.4 meters tall and are connected to each other. Wastewater flows in through the top pipes. The top 10 levels are filled with water hyacinth plants through which the wastewater will flow through over a period of 4 days. The number of days required to bring the constituents levels down to acceptable values for agriculture. Each level will additionally have lighting for plants indicated by the white, which is to help the plants grow, and have the plants vertically strapped to a steel mesh to easily allow periodic replacement. The last level will consist purely of UV lighting to kill pathogens, which the purified water will flow through and exit through the bottom pipe.
Now we shall get into the mathematics of the plant. We're considering the UV level as a separate reactor where the 10 levels of water hyacinth is one separator. The UV level is almost instantaneous, thus the time taken for the water to be purified depends on the water hyacinth process. Now, to look closely at the water hyacinth process, each level is 250 meter cubed. Now, when we look at each level is at 0.4 meters. Of this, the plant roots take up 0.3 meters, while the shoot is 0.1 meter. Thus, we'll be feeding in only half the volume of each level, which is 125 meter cubed, to ensure that the height of the water, which is 0.2 meter, will always flow through the roots. This ensures complete purification and will ensure clean water. We get into how much water our plant can actually purify. We have 10 levels, which amount to the previously mentioned 125 meter cubed times 10 equals 1,250 meter cubed of water. So assuming a 1,000 centimeter cube water equals 1 kg, 1,250 meter cube equates to 1,250,000 liters of water, which will be purified in our plant total at maximum capacity. This will be purified over a period of 4 days, which when we calculate, we get 3.6 liters of water per second.
Now back to the plant. Two issues you might have noticed that arises with this model is support and flow. Each level supports 125,000 kilograms of water along with the additional weight of the plant. As you might have noticed, all 11 levels only take up 4.4 meters. Our plant, which is 10 meters tall, has an additional 5.6 meters, which is evenly distributed to build concrete support and set up lighting for each level. Around 0.5 meters of support is possible for each level. Now, back to the drawing board.
The other issue is the flow of water, which has to be maintained at an exact level to keep the water flowing at a speed such that it traverses over the 10 levels over 4 days. This means that the water must stay in each level for 9.6 hours, as you can see. Now, it has to traverse each level for 9.6 hours. That's a distance of 25 meters. When calculated, that equates to 0.7 millimeters per second. Using the formula half mv squared, we get an energy of 0.03 joules. This, as you can tell, is too small to be provided for pumps. Thus, we will be angling each level to use the formula NGH to provide this energy.
Let me introduce the complex mathematician who is awkward and shy and confused, Mr. Sukhdeep. Be careful, sir.
Yeah. Mr. Kishkandy, thank you for having me on your show.
You. In the previous segment, we were talking about the complex mathematics involved about the wastewater treatment plant using aquatic plants. Now I want to know what the advantages of such plant is.
Of course. Now, the reactor design I showed in the previous segment, the advantage of this sort of design is that we're building up, as opposed to current aquatic plant purifiers which build along. This saves tremendous space, allowing more treatment to be done and build, resulting in more purifying of water. Also, by our design, we can have a continuous flow of wastewater coming in and purified water going out. Also, by using artificial lighting instead of using natural lighting as is usually done, we can also control the growth rate of the plants so we won't have to replace them as periodically. However, the thing with using water hyacinth is that it will need to be replaced, during which we cannot process wastewater. Our design also makes it easy to replace the hyacinth. There's the steel mesh. We can just remove the steel mesh, which will bring with it all the hyacinth, which we can then replace, which won't require any human interaction with the actual system and just requires a latch on each level. However, there are disadvantages to this. The main problem is that, as we said, the height needed to angle each level is so negligible in the nanometers to make it go at the speed required for it to go to 4 days. And we've also not considered the fluid resistance put up by the roots, which we'll have to actually process when we get to more in-depth design.
That was really interesting. Now, to look at where this can be implemented, we have already shot a segment of an interview from a very famous Indian agriculture scientist. Take a look. For further scope of implementation, I would like to invite a very educated man from the Isles of India, Mr. Random Scientist.
Actually, I'm Bangladeshi. Hello, my name is Random. You can call me Randy.
Before everything, #Randy. Google it. Continue, please.
I am a Bangladeshi national who works in India. I have a PhD in agricultural sciences and am passionate about the purification of wastewater for irrigation.
Could you tell us what sort of region this purification process would be a huge asset to?
Of course. The reason I was interested in pursuing this topic is because the region I work in, a state called Tamil Nadu, is a prime example for this sort of process.
Tamil Nadu. Here, right?
No, that's Bangladesh. It's there.
Oh, sorry. Moving on. Tell us what makes Tamil Nadu so special.
Tamil Nadu produces 10% of India's total amount of crop output, amounting to around 9 million tons of rice. However, over the past few years, they have faced heavy droughts to the point where they have gotten into feuds with neighboring states over water, which has made agriculture almost impossible. However, at the same time, Tamil Nadu also produces 7,000 million tons per day of wastewater. 1 kg of rice requires 1,500 liters of water. By converting just a mere fraction of wastewater to reusable water would be godsend. Its hot temperatures also make it perfect for the water hyacinth's growth cycle.
All this sounds good, but wouldn't it require a pre-existing foundation with good wastewater collection?
Which it does. Tamil Nadu has an incredible waste collection utilities in place in all major urban centers, but the problem lies in their treatment. I speak from experience when I say their treatment is subpar, and the excrement they process stays as excrement. If we could find a way to introduce a new process to convert this wastewater for agriculture purposes, it would have numerous social, economic, and sustainable benefits.
While this sounds viable in Tamil Nadu, wouldn't developing such a process just for one region be redundant?
Not at all. While I've primarily focused on that region, this can be implemented in various regions. For example, southern China and Brazil have suffered from the same water shortage problems while having an equivalent level of output of wastewater. They also have established waste collection stations with a lack of treatment facilities, so developing such a process would definitely have global implications.
Now, let us look at what our plants mean to Tamil Nadu. Assuming that the flow rate of water coming in remains constant and the plant is functioning 365 days of the year, then it should be able to produce 114,000 meter cubed of water. The basic requirement for production of 1 kilograms of rice is 1,500 meter cubed of water per ton. This implies that 76 tons of rice can be produced per annum using our plant. This is from only one plant. Cost of this plant is simple. Once the initial building has been built, the major cost only amounts to lighting and cost of replacing the plants, $3,000 and $15,000 respectively. This is one upper bound calculation. Comparing it to a normal plant, it costs about $400,000 to $500,000 to maintain. The output is not clean enough to be used for any purposes. Our plant, however, at a fraction of our maintenance cost, can feed a family at a cost of 50 cents. But we need to implement not only in one place, but multiple places. We need to change this perception that wastewater cannot be used effectively. Like your perception that I'm dressed formally. Let us change the perception of wastewater. Let us expand our project not only here, but throughout the state and the country. Remember, size doesn't matter, but the efficiency does. Let us implement this project throughout the world and change the world.